All right, welcome to the Explainer. If you're getting into electrochemistry, well, you've come to the perfect place. We're going to break down all the core concepts into a really powerful study guide. And hey, for all the students at CMS College of Engineering and Technology who are gearing up for exams, listen up. This one is definitely for you. Let's jump right in.
So here's our game plan. We'll kick things off with the basic definition, get our vocabulary straight, look at how the cells are actually built, and then wrap up with a super useful predictive tool called the electrochemical series. Okay, let's dive right into section 1. First things first, what in the world is electrochemistry?
When you boil it all down, it's really a two-way street. You can use electricity to make a chemical reaction happen. Think about charging your phone. Or you can have a chemical reaction that creates electricity. That's literally how a battery works. It's this awesome link between the chemical world and the electrical world.
Now, here's a key distinction you absolutely have to get. It's how electricity actually moves. In a metal wire, you've got tiny electrons zipping along. But in a solution, like salt water, it's not electrons. It's bigger, charged particles called ions doing all the work. And check this out. This is a bit weird. If you heat up a wire, it gets harder for electrons to flow, so conduction goes down. But if you heat up an electrolyte solution, the ions move faster and it actually becomes a better conductor. Totally opposite effects. All right, let's move on and define the key players in this whole setup. Getting these terms locked in is so important, especially for your exams. Okay, the electrode. Just think of it as the physical stage where all the action happens. It's the bridge that connects the outside wire to the inside solution. And the electrolyte? That's the liquid that the electrodes are sitting in. It's kind of like an ion soup that lets the charge move around and complete the circuit inside the cell. And here we go, probably the most important pair of words in this entire topic: anode and cathode. You have to know which is which. The easiest way, just remember this. Leo the lion says jur. Seriously, burn it into your brain. Leo stands for loss of electrons is oxidation, and that always happens at the anode. GR is gain of electrons is reduction, and that always happens at the cathode.
So let's talk about potential. Every electrode has this natural push or pull on electrons. We call that E. But that E value can change if it gets hotter or the solution changes. So to compare different electrodes fairly, we need a standard, right? Think of it like this. We all agree on what a foot or a meter is, so we can measure height. Well, in electrochemistry, when you see that little circle symbol, we call it E0, that's our standard. It means we're measuring under very specific, agreed-upon conditions, so we're always comparing apples to apples.
Okay, so we've got all the parts. Now let's look at the two main ways we can put them all together to build an actual cell.
This is a really big concept to get straight. On one side, we have electrolytic cells. Think of them as energy users. You have to plug them in, you feed them electricity to force a chemical reaction to happen. On the other side, we have galvanic cells. These are the energy makers. They use a chemical reaction that happens all by itself to create electricity. So, one uses power, the other makes power. Simple as that.
So let's zoom in on the cell that makes power. We're going to look at the classic example of a galvanic cell, one you will definitely see on your exams, the Daniell cell.
So, let's build it, step by step. Imagine we have two beakers. In one, we stick a zinc rod in some zinc sulfate solution. In the other, a copper rod in copper sulfate solution. Then we connect the two liquids with something called a salt bridge, and we connect the two metal rods with a wire. That's it. That's our cell.
Okay, so what actually happens? Well, over at the zinc anode, the solid zinc metal literally starts to dissolve. Each zinc atom loses 2 electrons and turns into a zinc ion that just floats away into the solution. That's oxidation, loss of electrons, LEO. So where do those electrons go? They travel through that wire all the way over to the copper cathode. Over there, copper ions that are already floating in the solution grab those 2 electrons, and when they do, they turn back into solid copper metal and plate onto the electrode. That's reduction, gain of electrons, GR.
Now, chemists don't want to draw that picture every single time, so they came up with this awesome shorthand to describe the whole thing. It's like a map. You read it from left to right. Anode on the left, cathode on the right. And see that double line in the middle? That's our salt bridge. Super simple once you know the code.
Okay, so we know the whole Daniell cell has a certain voltage. But that brings up a really tricky question. How do we figure out the voltage of just one side? Like just the zinc half cell all by itself?
And here's the thing, you can't. It's totally impossible. It's like trying to measure how high one hand is clapping. You can only measure the difference in potential between two things. So what do? We have to measure everything relative to one common starting point.
This is where a reference electrode comes in. Its entire job is to be our super stable, perfectly known baseline that we can measure everything else against. A really common one is the saturated calomel electrode. What's so interesting about this chart is that it shows even our standard can change a little bit depending on what's inside it. That's why scientists have to agree to use one specific version, like the saturated one, just to make sure everybody's results are consistent.
So once we measure all these different half cells against our standard, we can put them all together into an incredibly powerful tool that every chemistry student needs to know about. It's basically a ranked list. Think of it like a league table for the elements. At the very top, you have the elements that are champs at gaining electrons, and way down at the bottom, you have the ones that are desperate to just get rid of their electrons.
And this slide is the big payoff. This is why it all matters. The electrochemical series isn't just a boring chart you have to memorize. It's like a chemist's crystal ball. With this list, you can predict if a reaction will even happen on its own, you can calculate the exact voltage of any battery you can dream up, you can figure out which metals are stronger than others, all without ever stepping into a lab. It's an incredibly powerful, predictive tool. And because of this series, calculating the voltage, or EMF, of a cell becomes dead simple. You just look up the two values on the chart, and you subtract the potential of the anode from the potential of the cathode. Or even easier, using our shorthand notation, it's just the potential of the thing on the right minus the potential of the thing on the left. That's it. So to bring this all home, here's a final thought for you. If you wanted to build the most powerful battery possible, you'd need the biggest voltage you could get, right? The biggest potential difference. So looking at that series, which two elements are the farthest apart on that list? One that's at the very top and one that's at the very bottom. That's something for you to think about.